In this video, we're going to continue on with our discussion of the chain rule as it relates to partial derivatives. So let's suppose that we have a function f of two variables x and y here is equal to some constant c, where this actually specifies y as a function of x. So we're supposing again that y is a function of x here. Those are not two independent variables. If we wanted dy dx without explicitly solving for y in terms of x, we do have a method from first semester calculus called implicit differentiation. However, with our new chain rule for multivariable functions, we actually have an easier method to do this. So we have an easy formula for dy dx. So let's write out what that is real quick. We want to take the derivative of the function f with respect to x. Well, notice that we have f is a function of x and y. And of course, x is a function of x and y is a function of x, given our assumption up here that, again, y is a function of x. So to do this using our partial derivatives chain rule that we just worked out in the previous video, we have the derivative of f with respect to x is the partial of f with respect to x times the derivative of x with respect to x plus the partial of f with respect to y times dy dx. Well, what is the partial of f with respect to x? Well, that's just whatever that is. But then what is the derivative of x with respect to x? Well, that's just 1. And then we have plus the partial of f with respect to y times dy dx. That's exactly what's written here on the left side. Remember that f sub x and f sub y are just our notations for the partial of f with respect to x and the partial of f with respect to y, respectively. And of course, our function in the first place was f of x comma y is equal to c. So we take the derivative on the right-hand side, and that constant, the derivative of that constant is just 0. So that's how we get our formula here, f of x, f sub x plus f sub y times dy dx is equal to 0. Then we can just solve for dy dx. So when we do that, we get dy dx is equal to negative of the partial of f with respect to x divided by the partial of f with respect to y. So that's going to be our formula. And let's do that. So let's do that for our first example. We're going to suppose that the equation arctan of x squared y is equal to x plus xy squared. And that implicitly describes y as a function of x. We want to calculate y prime. Well, first thing you should do is move everything over to write it in terms of, So we want to move everything to one side. Minus x minus xy squared is equal to 0. So we have everything is equal to some constant, in this case, the constant 0. So f is this entire thing on the left side. Dy dx is equal to negative partial of f with respect to x over partial of f with respect to y. Okay, so this is negative of, let's take the partial of f with respect to x. The derivative of arctangent of x squared y is 1 over 1 plus what is inside that function squared, so x squared y all squared. Then we have to multiply that by the derivative of the inside of that function, so the derivative of x squared y with respect to x, the partial derivative of x squared y with respect to x is 2xy. Then the partial derivative, so we're done with the arctan x squared y part. So now we take the partial derivative of negative x with respect to x, and we get minus 1. Take the partial derivative of xy squared with respect to x, and we get minus y squared. And that's exactly what we have up in the numerator here. And so then we need to divide by the partial of f with respect to y. So let's do that real quick. Let's see, that is 1 over 1 plus x squared y squared times the partial derivative of x squared y with respect to y. So that is just x squared. And then the partial derivative of negative x with respect to y is 0. And the partial derivative of negative x squared with respect to y is negative 2xy. And so this is our solution. And you could just do this in the way that you knew how from the first class, or you could try, and see if you get this solution, the same solution. All right. Let's go on and do a couple more examples. We have a similar implicit differentiation if we have z is a function of two independent variables, x and y. This time we get two different formulas because we have to take the derivative of f with respect to x, and we end up with this formula. We take the derivative with respect to of f with respect to y, we end up with this formula. And then this implies these two formulas right here. But this is again, if we have an implicit function on three variables, x, y, and z, where this describes z as a function of two independent variables, x and y, then we get those formulas for partial of z with respect to x and partial of z with respect to y. All right. Let's do this example 5. Let's do the partial of z with respect to x. So this is the first formula up here. So partial z with respect to x is equal to negative partial of f with respect to x divided by partial of f with respect to z. Our formula is x cubed plus y cubed plus z cubed plus 6xyz, right? We need to move everything except for the constant over to one side, and this is all equal to 1. So we can leave that 1 on the right hand. So this is our function f of the three variables x, y, and z. All right, so partial of z with respect to x is negative of, all right, what's the partial of f with respect to x? Well, we get 2x. Oh, sorry. This is supposed to be a 3. I was very confused for a moment. That was supposed to be x cubed plus y cubed plus z cubed. All right. So we take the partial of f with respect to x. We get 3x squared. The partial of y cubed with respect to z with respect to x to y is the partial derivative of y cubed with respect to x is 0. The partial derivative of z cubed with respect to x is 0. The partial derivative of 6xyz with respect to x is plus 6yz. All right, and we divide all of that by the partial with respect to z. So the partial derivative of x cubed with respect to z is 0. Partial derivative of y cubed with respect to z is 0. Partial derivative of z cubed is 3z squared. And then the partial derivative of 6xyz with respect to z is plus 6xy. And this gets our exact expression down here. So this is our solution. I'm going to let you work out the partial derivative of z with respect to y on your own. You just use this formula right there on the right. So go ahead and take time to do that on your own, and then move on to this final example 6 here. So let's suppose that the equation yz plus x natural log of y is equal to z squared implicitly describes z as a function of the two variables x and y. So we have all the conditions that we need for our above formulas. We're going to find the values of zx and zy when x, y, and z is 1, 1, 1. First off, we need to write everything out in terms of, or in the form that we need it in. So this is yz plus x ln of y minus z squared is all equal to 0. And then we want the partial of z with respect to x. And this was negative f sub, well, just move on up here. The partial of z with respect to x is negative partial with respect to x over partial with respect to z. All right, and what is that? Well, what is the partial with respect to x here? The partial derivative of y squared with respect to x is 0. The partial derivative of x times ln of y with respect to x is just positive ln of y minus the partial of z squared with respect to x is 0, all divided by the partial of f with respect to z. So partial of y squared with respect to z is 0. The partial of x ln of y with respect to z is 0 because there's no z in there. And the partial of negative z squared is negative 2z. Plug in all of your values. So this is negative of ln of 1 because we're given that y is 1. All over negative 2 times 1. Well, this is negative of 0 over negative 2, which is just 0, which we have right here. And again, I'll leave it up to y'all to find z sub y at the point 1, 1, 1. And you should end up getting 2. And that will end this video.